Look up at the night sky, and you'll see a sea of stars, pinpricks of light stretching endlessly across the cosmos. But hidden within that vast darkness lie structures so strange, so baffling, they defy everything we thought we knew about the universe. Enormous rings of galaxies spinning in perfect harmony, voids so empty they stretch for hundreds of millions of light years, and cosmic filaments weaving through space like threads in a tapestry we can't quite unravel. These aren't just random quirks of nature, they're puzzles written in the language of the universe itself, waiting for us to decode their secrets. Imagine standing at the edge of one of these galactic mysteries, feeling the sheer scale of it humbling your very existence. Some of these formations are so colossal, they make our Milky Way look like a speck of dust. Others behave in ways that leave even the most brilliant astronomers scratching their heads, as if the universe is playing a game we don't yet understand the rules to. From the eerie silence of the Boots void to the hypnotic dance of the Hercules-Corona Borealis Great Wall, these structures challenge our deepest assumptions about how space and reality itself works. And that's exactly what we're diving into today. 25 of the most mind-bending, spine-tingling enigmas the cosmos has to offer. Each one a story written in starlight and shadow, each one pushing the boundaries of what we thought was possible. Some might hold the keys to dark matter, others could rewrite the laws of physics, but all of them remind us just how little we truly know about the grand stage we call the universe. So buckle up, because we're about to take a journey through the strangest corners of space, where the rules bend, the questions multiply, and the answers, well, they might just change everything. Hidden in the depths of space, stretching so far it could contain tens of thousands of galaxies like our own, lies the Hercules-Corona Borealis Great Wall, a structure so vast it redefines the meaning of colossal. Picture a cosmic ribbon woven from galaxies 10 billion light-years from end to end. That's nearly 1/10 the size of the entire observable universe. Scientists stumbled upon this behemoth while mapping gamma-ray bursts, flashes of energy so powerful they serve as cosmic breadcrumbs, marking the locations of distant galaxies. What they found wasn't just a cluster or a supercluster, but something far more perplexing. A gargantuan formation of galaxies aligned in a way that shouldn't exist. According to everything we know about cosmology, the universe should look roughly the same no matter where you observe it, a principle called homogeneity. Yet here's this wall defying that rule with its sheer scale. If structures like this can form, it means our understanding of gravity, dark matter, or even the very fabric of space-time might be incomplete. Some theories suggest dark energy, the mysterious force accelerating the expansion of the universe, could have played a role, sculpting this wall like an invisible hand shaping cosmic dough. Others wonder if we're seeing a flaw in our measurements, a trick of perspective that makes this structure appear more significant than it truly is. But here's where it gets even stranger. The Great Wall isn't just big, it's old. Its light has traveled so far that we're seeing it as it existed when the universe was barely a third of its current age. How could something so immense have formed so early? Current models of cosmic evolution struggle to explain it. It's as if the universe built a skyscraper overnight, with no blueprints or scaffolding, just raw, inexplicable ambition. And that's what makes this wall more than just a curiosity. It's a silent challenge, a cosmic dare for us to rethink the rules. Maybe the universe isn't as uniform as we thought. Maybe there are processes at work beyond our wildest theories. Every time we look deeper into the cosmos, it seems the answers only lead to bigger questions. The Hercules-Corona Borealis Great Wall isn't just a structure, it's a mystery written across the sky, waiting for us to decipher its secrets. If the Hercules-Corona Borealis Great Wall left you questioning the limits of cosmic scale, wait until you meet its rival, the Sloan Great Wall. This staggering filament of galaxies isn't just another large structure. It's a cosmic spine stretching 1.4 billion light-years, weaving through the universe like a river of starlight. Discovered in 2003 by astronomers analyzing data from the Sloan Digital Sky Survey, this wall isn't a single solid mass but a chain of superclusters, colossal families of galaxies bound together by gravity, each containing thousands of individual galaxies like our own Milky Way. What makes the Sloan Great Wall so extraordinary isn't just its size, though that alone is mind-bending, but the way it defies one of astronomy's foundational ideas, the cosmological principle. This principle states that, on large enough scales, the universe should look roughly the same no matter where you're observing from. No single region should stand out as Chinese letter, or unusual. Yet here we have this immense structure, its galaxies aligned in a pattern so vast it seems to thumb its nose at that very idea. If the universe is supposed to be uniform, how did something this concentrated and organized come to exist? One theory suggests that dark matter, the invisible scaffolding of the cosmos, played a key role in shaping the Sloan Great Wall. As the universe expanded after the Big Bang, dark matter's gravitational pull could have drawn galaxies together into these immense filaments like beads on a string. But even that explanation falls short when we consider the wall's sheer scale. Could dark matter alone have orchestrated something this enormous, or is there some other force, some unknown influence helping to stitch these galaxies together? And then there's the question of perspective. From our vantage point on Earth, the Sloan Great Wall appears as a Chinese letter structure. But is it truly a single, continuous formation, or are we seeing a chance alignment of smaller clusters, a trick of cosmic geometry? Some researchers argue that if we could observe it from a different angle, the wall might dissolve into separate pieces. Others counter that the statistical likelihood of so many superclusters lining up by accident is vanishingly small. The debate itself is a testament to just how little we understand about the universe's largest structures. With every discovery, the cosmos seems determined to surprise us, offering up puzzles that challenge our most deeply held theories. The Sloan Great Wall isn't just a curiosity, it's a challenge, a reminder that for all our knowledge, the universe still has secrets waiting to be uncovered. Just when we thought the universe couldn't surprise us any further, astronomers stumbled upon something that defies logic: the giant arc. Picture a celestial crescent stretching 3.3 billion light-years across the cosmos, a chain of galaxies so vast it would take light, the fastest thing in existence, more than 3 billion years to travel from one end to the other. Discovered in 2021 by a team analyzing light from distant quasars, this structure isn't just large, it's a direct challenge to our understanding of how the universe organizes itself. What makes the giant arc so extraordinary isn't just its size but its shape. Unlike the walls and filaments we've seen before, this structure forms a near-perfect curve, as if someone drew a smile across the cosmos. Galaxies, galaxy clusters, and clouds of gas align along this arc with eerie precision, hinting at some unseen force orchestrating their placement. But here's the problem: according to our best models, structures this large and coherent simply shouldn't exist. The laws of physics suggest that matter should distribute itself more randomly across such vast distances, not clumped together in these sweeping, symmetrical patterns. The controversy surrounding the giant arc centers on one burning question: is this structure real, or is it a cosmic illusion? Some scientists argue it's a statistical fluke, a chance alignment of galaxies that only appears to form an arc from our perspective. After all, when you're mapping something as immense as the observable universe, coincidences can look intentional. But others counter that the odds of so many galaxies lining up so perfectly by pure chance are astronomically low. If the arc is real, it would mean our models of galaxy formation, and even the fundamental principles of cosmology, might need a radical overhaul. One theory suggests that the giant arc could be a fossil from the universe's earliest moments, a relic of primordial sound waves left over from the Big Bang. These waves, rippling through the infant cosmos, might have nudged matter into these vast, curving arrangements. Another possibility involves dark matter's gravitational influence, sculpting the arc over billions of years like an invisible hand shaping cosmic clay. But even these explanations struggle to account for the arc's sheer scale and symmetry. What's clear is this: if the giant arc holds up to further scrutiny, it could rewrite the story of how galaxies form and cluster. It might hint at unknown forces or hidden laws governing the large-scale structure of the universe. Or perhaps it's a sign that we're missing something fundamental in our equations, a blind spot in our cosmic vision. For now, the giant arc remains one of the universe's most tantalizing puzzles, a silent question mark hanging in the dark, daring us to look deeper. Among the cosmic wonders that defy expectations, Hoag's object stands out as a celestial masterpiece, a galaxy so perfect it looks almost artificial. Unlike the spiraling arms of the Milky Way or the chaotic shapes of irregular galaxies, this enigmatic structure presents itself as a pristine ring of blue young stars encircling a golden, spherical core, with a vast, empty gap separating the two. Discovered in 1950 by astronomer Arthur Hoag, who initially mistook it for a planetary nebula, this galaxy's symmetry is so striking it feels like an artist's deliberate creation rather than a natural formation. What makes Hoag's object even more intriguing is its rarity. Out of the hundreds of billions of galaxies observed, only a handful exhibit this perfect ring structure, and none match its clarity. The core, packed with older, reddish stars, sits like a jewel at the center, while the outer ring blazes with the blue light of newborn stars, stellar nurseries where gas and dust collapse into brilliant young suns. The gap between them spans roughly 100,000 light-years, a void so clean it's as if some cosmic force swept away all traces of stars or debris. How did this cosmic oddity come to be? One leading theory points to a violent past, a galactic collision. Billions of years ago, a smaller galaxy might have plunged straight through the heart of Hoag's object, its gravitational pull rippling the surrounding gas into a wave that triggered star formation in a perfect ring. Alternatively, the core could have experienced a period of instability, sending shockwaves outward that compressed gas into the ring we see today. Yet both theories struggle to explain the sheer precision of the structure. Collisions usually leave behind chaotic debris, not flawless symmetry. Another possibility involves resonance, a phenomenon where gravitational forces align material into stable, repeating patterns like the grooves in a vinyl record. If the core's rotation synchronized with the outer disk, it could have sculpted the ring with mathematical precision. But even this explanation leaves unanswered questions. Why don't we see more galaxies like this if the process is possible? And what stopped stars from forming in the gap? The mystery deepens when we consider that Hoag's object isn't entirely alone. Nestled within its dark gap, faint traces of another ring have been spotted, hinting at a history even more complex than we imagined. Some astronomers wonder if we're witnessing multiple generations of rings, layered like tree rings, each telling a different chapter of this galaxy's enigmatic life. What's certain is that Hoag's object challenges our assumptions about galactic evolution. It's a reminder that the universe has a flair for the extraordinary, crafting rarities that push the boundaries of what we consider possible. Whether it's the product of a cataclysm, a delicate balance of forces, or something entirely unknown, this cosmic jewel keeps its secrets closely guarded, a perfect enigma floating in the void. Deep in the constellation of Bootes lies one of the most unsettling cosmic mysteries, a region so empty, so unnervingly dark. It's earned the nickname the Great Nothing. The Bootes void spans a staggering 330 million light-years, a volume of space so vast it could contain thousands of galaxies like our own. Yet when astronomers peer into it, they find almost nothing, just a handful of galaxies floating in an ocean of emptiness, like a few scattered islands in a desert the size of the universe itself. How does something this barren exist? The void's discovery in the 1980s sent shockwaves through the astronomy community. Imagine pouring sand onto a table, expecting an even sprinkle, only to find a gaping hole where barely a grain has fallen. That's the Boots void. It defies our understanding of cosmic structure, where matter should be distributed relatively evenly, not missing entirely from such an enormous region. Some theories suggest it could be the remnant of a quantum fluctuation in the early universe, a bubble of slightly lower density that, over billions of years, stretched into this terrifying expanse as space expanded. Others speculate it might be the work of dark energy, pushing matter apart faster than gravity can pull it together. But here's where it gets even stranger. The few galaxies that do dwell inside the void aren't arranged randomly. They cluster in a peculiar tube-like formation, as if huddling together for warmth in the cosmic cold. This raises a haunting question. Did something evacuate the void, leaving only these survivors behind? Or is their alignment a clue to an even deeper mystery, like the fingerprints of forces we haven't yet discovered? And then there's the silence. The Boots void doesn't just lack light. It lacks the faint radio whispers of hydrogen gas, the usual soundtrack of interstellar space. It's as if the universe hit mute in this pocket of darkness. That silence has led some to wonder if the void isn't just empty. It might be older than the space around it, a relic from a time before stars. If true, it could be a window into the universe's earliest moments, a frozen bubble of near-nothingness that escaped the frenzy of cosmic evolution. Yet for all its eeriness, the Boots void isn't entirely unique. Smaller voids have been found throughout the cosmos, woven into the large-scale structure of the universe like holes in Swiss cheese, but none match its scale or its defiance of expectation. It stands as a reminder that for every rule we think the universe follows, there's an exception lurking in the shadows, or in this case, the absence of them. The Great Nothing isn't just empty space, it's a question mark written in the dark, challenging us to explain how nothingness can be so vast and what it means for everything else. Rising from the heart of our Milky Way like twin ghosts of a forgotten cosmic eruption, the Fermi bubbles stretch 50,000 light-years into space, one erupting north of the galactic plane, the other south. These colossal structures, discovered in 2010 by the Fermi Gamma-Ray Space Telescope, glow with high-energy radiation, their edges sharply defined against the darkness as if carved by some unseen blade. Picture two vast balloons of seething particles, each large enough to contain thousands of solar systems, towering over the galaxy we call home. What makes these bubbles so extraordinary isn't just their size, it's the fact that we're living right next to them, yet their origins remain fiercely debated. The leading theory points to Sagittarius A, the supermassive black hole at our galaxy's core. Somewhere between 6 and 26 million years ago, this sleeping giant might have awakened in a violent feeding frenzy, devouring enormous amounts of matter and belching out jets of energy so powerful they punched through the galactic disk, inflating these bubbles like cosmic bellows. Imagine a tsunami of particles racing outward at nearly the speed of light, their shockwaves heating surrounding gas to millions of degrees, a cataclysm that would have lit up the Milky Way like a beacon. But here's where the mystery deepens. The bubble's gamma-ray emissions don't match typical black hole outbursts. Instead of a smooth gradient, their edges are strikingly crisp, suggesting something far more sudden. Perhaps a single, titanic explosion rather than a prolonged eruption. This has led some scientists to propose an even wilder scenario. That Sagittarius A wasn't just active in the past. It might have briefly transformed into a quasar, a phenomenon we usually associate with galaxies billions of light-years away. If true, our humble Milky Way could have once rivaled the brightest objects in the universe. its heart blazing with light as it shredded stars and gas clouds in a feeding frenzy of unimaginable scale. Yet not everyone is convinced. Alternative theories suggest the bubbles could be the accumulated remains of countless supernovae, their combined energy sculpting these structures over eons. Others speculate about dark matter annihilation, exotic particles colliding and releasing energy in a process we've yet to fully understand. Even the bubble symmetry poses a puzzle. Why are they so perfectly aligned with the galactic center, and what stopped their expansion so abruptly? One clue might lie in the gas filaments that weave around the bubble's edges, resembling the seams of a stitched celestial fabric. These filaments, crackling with magnetic energy, could be the scars of an ancient battle, the moment the eruption's fury met the resistance of the Milky Way's halo. Or perhaps they're evidence of ongoing activity, hints that Sagittarius isn't as dormant as we think. What's certain is that the Fermi bubbles force us to reconsider our galaxy's past. They suggest a time when the Milky Way wasn't the quiet spiral we know today, but a place of unimaginable violence, and they remind us that even our cosmic neighborhood holds secrets capable of rewriting history, one gamma-ray photon at a time. Right now, two cosmic titans are racing toward each other at 250,000 miles per hour, and yet none of us will live to see their inevitable embrace. The Milky Way and Andromeda, our nearest galactic neighbor, are locked in a gravitational dance that will end 4 billion years from now in a collision of unimaginable scale. Picture this: two spiral galaxies, each containing hundreds of billions of stars, slowly merging into a single, radiant behemoth some astronomers have nicknamed Milkdromeda. Far from the apocalyptic crash you might imagine, this event will be more like a celestial ballet, a slow-motion rearrangement of the cosmos where gravity, not impact, does the heavy lifting. Here's the surprising truth: when galaxies collide, the stars inside them barely notice. The distances between stars are so vast that direct collisions are almost unheard of. Instead, the real drama unfolds in the gravitational tides, where immense forces twist and stretch the galaxy's shapes like taffy. Andromeda's first pass will warp the Milky Way's spiral arms into chaotic streamers, scattering stars into long, glowing ribbons across the sky. Over billions of years, the two galaxies will swing past each other again and again, each encounter stripping away their old structures until they finally settle into a single, elliptical galaxy, a golden island in the cosmic sea. What's even more remarkable is what these collisions create. The interstellar gas and dust jostled during the merger will trigger fireworks of star formation, igniting nurseries where new suns blaze to life by the millions. Ancient red giants might find themselves neighbor to brilliant blue newborns, a stellar generation gap written in light. And amid this chaos, our own solar system could be flung to the galaxy's outer edges, or, in a far smaller chance, ejected into intergalactic space entirely. Yet Earth, if it still exists, would likely survive unscathed. The real spectacle would be the night sky, a canvas splashed with unfamiliar constellations, Andromeda's stars merging with our own until the two are indistinguishable. But why do galaxies collide so peacefully? The answer lies in their strange composition. Despite their dazzling starry disks, galaxies are mostly empty space, their mass concentrated in invisible halos of dark matter that interpenetrate like ghosts. It's these halos that dictate the merger's rhythm, their gravitational pull orchestrating the slow-motion dance. Even the supermassive black holes at their cores will eventually spiral together, unleashing ripples in space-time gravitational waves before merging into a single, more massive singularity. This future merger isn't just a curiosity, it's a reminder that destruction and creation are two sides of the same cosmic coin. The same forces that tear galaxies apart also seed them with new life. And while humanity won't witness Milkdromeda's birth, we're uniquely placed to study its precursors, galaxies like the Antennae, whose tangled arms show us snapshots of this process in action. Each collision we observe is a clue to our own distant fate, a testament to the universe's endless capacity for reinvention. The Milky Way and Andromeda aren't headed for an end, they're on course for a second act, one that will transform them into something entirely new. Galaxies don't just drift randomly through the cosmos, they move, pulled by the invisible strings of gravity. But in 2008, astronomers stumbled upon something that defied all expectations. A strange, coordinated motion of galaxy clusters, all streaming toward the same unseen point in space as if beckoned by a cosmic siren. They called it the dark flow. Imagine throwing a handful of leaves into a river most would scatter, carried by local currents. But if every single leaf suddenly surged in the same direction, you'd suspect something powerful was pulling them beneath the surface. That's the essence of the dark flow. Across billions of light years, entire clusters of galaxies, along with their embedded dark matter, are racing toward a region near the constellations Centaurus and Hydra at speeds exceeding 2 million miles per hour. And here's the unsettling part, there's nothing there. No supercluster, no concentration of mass, just empty space. So what's tugging them? One hypothesis is as breathtaking as it is unsettling. The pull might be coming from beyond the observable universe. Just past the cosmic horizon, the limit of what we can see, there could lurk an unimaginably massive structure, a supercluster of galaxies or even a rift in spacetime itself, warping the fabric of reality on scales we can't fathom. Some theories suggest our universe might border another in a vast multiverse, their gravitational fields leaking across the divide like whispers through a wall. If true, the dark flow could be our first glimpse of something profoundly alien, proof that the cosmos stretches far beyond what our telescopes will ever capture. But not everyone is ready to rewrite physics. Skeptics argue the flow could be an illusion, a distortion caused by incomplete data or overlooked variables in our measurements of cosmic microwave background radiation, the afterglow of the Big Bang. Others propose more conservative explanations, like flaws in our models of dark matter. Perhaps its distribution isn't as uniform as we thought, and vast, undetected concentrations are skewing the motion of galaxies on these scales. Yet the most tantalizing clue lies in the flow's scale. It isn't localized, it stretches across the observable universe, suggesting the source, if it exists, operates on a level far beyond anything we've encountered. That raises a chilling possibility. What if the dark flow isn't just pulling galaxies? What if it's pulling everything, including us, toward some distant, unfathomable destiny? For now, the phenomenon remains one of cosmology's deepest puzzles. It challenges our understanding of gravity, of the universe's boundaries, even of reality itself. Whether it's a sign of unseen dimensions, a flaw in our equations, or something entirely unexpected, the dark flow reminds us that the cosmos still holds mysteries too vast to ignore. And as we strain to decipher its secrets, one thing becomes clear: the universe is moving, and it might be heading somewhere we can't yet see. Forget what you learned about the Milky Way floating alone in space. We're actually part of something far grander. Nestled within a sprawling celestial metropolis spanning 520 million light-years, our galactic home belongs to the Laniakea Supercluster, a name from Hawaiian meaning immense heaven. This isn't just a random collection of galaxies. It's a dynamic, interconnected web where gravity acts like cosmic traffic lines, guiding entire galaxies along invisible highways toward dense hubs of matter. Picture a vast river system with galaxies as leaves carried by its currents, except these currents flow through the fabric of spacetime itself. Mapping Laniakea required rethinking how we define cosmic structures. Traditional methods relied on visible clusters, but astronomers recently turned to something subtler: the peculiar motions of galaxies. By tracking how thousands of galaxies drift, not just with the universe's expansion, but against it, they uncovered gravity's hidden architecture. Like water circling a drain, galaxies within Laniakea all creep toward a gravitational focal point known as the Great Attractor, a mysterious region obscured by our own galaxy's dust. These collective movements reveal supercluster borders more clearly than mere proximity ever could. What's striking isn't just Laniakea's scale, but its structure. Filaments of galaxies thread between nodes like pearls on strings, connecting massive clusters such as Virgo and Hydra Centaurus. Between them lie vast voids, deserts of near-nothingness, making superclusters resemble cosmic foam. Our Milky Way resides on the outskirts of Laniakea, in a quieter suburban arm far from the bustling core. Yet even here, we're not stationary. Every second, we're pulled hundreds of miles closer to Norma Cluster, Laniakea's brightest gathering, proving that gravity's tugs shape our path across the eons. But Laniakea isn't the end of the story. It's just one thread in an even larger tapestry. Recent studies suggest it may be part of a still greater structure, perhaps linked to the Shapley supercluster, the universe's most massive known concentration of galaxies. This revelation hints at hierarchies upon hierarchies, a fractal universe where each scale unveils new patterns. Ultimately, Laniakea redefines our place in the cosmos. We're not just inhabitants of a galaxy, we're passengers in a gravity-bound voyage riding currents older than stars. And as we map these flows, we're decoding the universe's hidden blueprints, one galaxy's drift at a time. Hidden behind a curtain of stars and dust in our own galaxy lies one of the most powerful gravitational mysteries in the cosmos, the Great Attractor. This enigmatic region, located roughly 250 million light-years away in the direction of the constellation Centaurus, exerts an irresistible pull on not just the Milky Way, but thousands of other galaxies in our cosmic neighborhood. Picture a cosmic whirlpool, its invisible currents dragging entire galaxies toward it at speeds exceeding 1 million miles per hour. Yet for decades, this gravitational behemoth remained nearly invisible to us, obscured by the Milky Way's own bulk, a region astronomers call the zone of avoidance. The zone of avoidance isn't just a minor inconvenience, it's a blind spot spanning about 20% of the night sky, where our galaxy's dense clouds of gas and dust block nearly all visible light from beyond. Trying to study the Great Attractor through this murky veil is like trying to spot a lighthouse through a thunderstorm, but astronomers are nothing if not resourceful. By switching from optical telescopes to instruments that detect radio waves, infrared light, and X-rays wavelengths that can pierce the cosmic fog, they've begun to glimpse what lies behind the curtain. What they've found is both breathtaking and perplexing. A confluence of immense galaxy clusters, their combined gravity weaving a web strong enough to tug on the fabric of spacetime itself. One leading theory suggests the Great Attractor isn't a single object, but a dense knot in the cosmic web, a place where multiple superclusters intersect. At its heart lies the Norma Cluster, a gathering of hundreds of galaxies, but even its considerable mass can't fully explain the observed pull. That's led scientists to look even farther, to the Shapley Supercluster, a staggering collection of galaxies over 650 million light-years away. Some believe Shapley's gravity might be amplifying the Great Attractor's influence, like a massive anchor pulling on a chain of smaller weights, but here's where the plot thickens. Recent measurements suggest the Great Attractor's pull might be part of something even larger, the dark flow, that mysterious motion of galaxy clusters toward some unseen horizon. Could these phenomena be connected? Is the Great Attractor itself being pulled towards something greater, like a link in a cosmic chain we're only beginning to grasp? The answers could rewrite our understanding of gravity's reach and the universe's structure on the grandest scales. For now, the Great Attractor remains a reminder that even in our own cosmic backyard, the universe keeps its most profound secrets just out of sight. Every new observation peels back another layer, revealing not just answers, but deeper questions about the forces shaping our journey through the cosmos. Most galaxy clusters are like cosmic graveyards, vast cities of ancient, red stars where new births are nearly unheard of. But the Phoenix cluster defies this fate with an explosive burst of creation, churning out stars at a rate hundreds of times faster than our own Milky Way. At its heart lies a supermassive black hole, but unlike most of its kind, this one isn't stifling star formation. It's fueling it in a spectacular paradox that's rewriting our understanding of how galaxy clusters evolve. What makes the Phoenix cluster so extraordinary is its cooling flow, a phenomenon that should be impossible under traditional models. Typically, the supermassive black holes at the centers of galaxy clusters act like cosmic blowtorches, pumping out jets of energy so powerful they heat the surrounding gas to millions of degrees, preventing it from cooling and collapsing into new stars. But in Phoenix, something's gone wrong, or perhaps spectacularly right. Here, vast rivers of gas are cooling at breakneck speed, condensing into dense clouds that ignite into brilliant blue frenzies of stellar birth. It's as if the universe's usual rules have been flipped on their head, creating a celestial nursery where there should only be silence. This anomaly forces us to rethink how black holes interact with their surroundings. In most clusters, feedback loops between the black hole's energy and the surrounding gas create equilibrium, a balance that suppresses star formation. But Phoenix's black hole seems to be slacking, its outburst either too weak or too sporadic to keep the gas hot. The result, a cooling cascade so intense it's forming stars at a rate of about 700 per year, compared to the Milky Way's modest 1 or 2. Yet even this explanation might be too simplistic. Some astronomers suggest the real story lies in the cluster's turbulent history. Mergers with smaller galaxies could have funneled fresh gas into the core, overwhelming the black hole's ability to regulate it. Others propose the cooling flow isn't just a failure of feedback, it's a glimpse of a rare phase in a cluster's life cycle, a fleeting moment when the scales tip from stagnation to rebirth. The implications ripple far beyond Phoenix. If cooling flows can reignite star formation on such epic scales, it means galaxy clusters aren't just static relics, they're dynamic ecosystems capable of second acts. It challenges the idea that clusters must inevitably fade into red and dead retirement, suggesting instead that under the right conditions, even the oldest structures can experience celestial spring. And for astronomers, that's an invitation to scour the cosmos for more outliers, more rule breakers, more phoenixes, because if one cluster defies expectations, who's to say others aren't hiding in plain sight? What's certain is this: the Phoenix cluster isn't just an oddity. It's a testament to the universe's stubborn refusal to be pigeonholed, a reminder that even our best models are just sketches of a reality far richer and more unpredictable than we dare imagine. Amid the chaos of the cosmos, where most nebulae sprawl in organic swirls of gas and dust, the Red Rectangle Nebula stands apart, a jewel of geometric precision floating 1,500 light-years away in the constellation Monoceros. At first glance, it looks less like a cosmic cloud and more like an artisan's creation. Two luminous cones of crimson light meeting at a central star, their edges so sharp they form what appears to be a perfect three-dimensional rectangle. This isn't just a trick of perspective, it's the result of one of the most meticulously orchestrated stellar processes we've ever witnessed. The nebula's mesmerizing shape comes from a phenomenon known as bipolar outflow. At its heart lies HD 44179, a dying star in the final stages of its life. Unlike the violent explosions of supernova, this star is bowing out with eerie elegance, shedding its outer layers in two opposing jets of gas and dust. Those jets collide with a dense disk of material encircling the star, a relic from its earlier, stable life, forcing the outflow into that unmistakable X shape. But what's truly astonishing is the chemistry at play. The red rectangle glows crimson not just from hydrogen, the usual suspect in nebulae, but from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons. These intricate compounds, often found in soot on Earth, are being forged in the star's death throes, painting the nebula in hues so vivid they defy the darkness of space. And here's where it gets personal. HD 44179 isn't some exotic stellar oddity, it's a mirror to our own sun's future. In about 5 billion years, our star will embark on a similar journey, shedding its outer layers to form a planetary nebula. But will it look like the red rectangle? Probably not. The precision of this nebula's shape hinges on factors we're still unraveling. The star's rotation, the structure of its debris disk, even the subtle tug of a faint companion star lurking nearby. What makes the red rectangle so rare is the alignment of these cosmic variables, like a celestial Rube Goldberg machine firing flawlessly. Yet the mysteries don't end there. Nestled in the nebula's core, astronomers have detected an unexpected signature: the spectral fingerprints of complex organic molecules, including anthracene and pyrene. These are the building blocks of life's chemistry, suggesting that even in death, stars like HD 44179 might be seeding the universe with the ingredients for something new. It's a poetic thought that this ruby in the sky isn't just a tomb, but a cradle for possibilities we've yet to imagine. The Red Rectangle Nebula is more than a cosmic curiosity. It's a reminder that the universe adores patterns even in chaos. From the mathematical perfection of its shape to the alchemy of its dust, this nebula challenges us to rethink how stars live, die, and perhaps even how they give birth to what comes next. Gaze upon the Black Eye Galaxy, and you'll understand why it's earned its haunting nickname. Wrapped around its glowing core like a celestial bruise, a dense lane of cosmic dust swallows the light of countless stars, leaving a shadowy gash against the spiral's brightness. Officially catalogued as M64, this galaxy isn't just a pretty cosmic oddity. It's a crime scene bearing the scars of a violent past that still echoes in its very motion. What makes M64 truly strange isn't just its appearance, but its anatomy. Unlike most galaxies, where stars and gas rotate in unison like a spinning plate, the Black Eye Galaxy is divided. Its inner region, a compact disk of stars spanning about 3,000 light-years, spins in one direction, while the outer arms, stretching 80,000 light-years across, surge the opposite way. It's as if the galaxy is caught in a cosmic tug-of-war, with two halves stubbornly refusing to sync. Astronomers trace this chaos back to a cataclysmic merger. Billions of years ago, a smaller galaxy likely plunged straight through M64's heart, its gravity ripping apart the existing order. As the intruder's debris mixed with the larger galaxy's gas and dust, it created that infamous dark lane, a swirling graveyard of stellar wreckage. But the collision didn't just leave a mark, it rewired the galaxy's mechanics. The incoming galaxy's angular momentum, like a twist in a cosmic whirlpool, could have flipped the outer disk's rotation while the inner core held its ground. Yet the drama doesn't end there. Nestled within that dark dust belt, new stars are being born at a frantic pace. The very material that gives M64 its eerie appearance is also its most fertile ground, compressing pockets of gas until they ignite into brilliant blue clusters. It's a paradox: destruction and creation woven together, proving that even in chaos, the universe finds a way to build anew. Peering into the Black Eye Galaxy isn't just studying a distant spiral. It's witnessing the aftermath of a celestial collision, one that reshaped an entire galaxy's destiny. Every counter-rotation, every dust-choked star tells a story of violence and renewal, a reminder that even the cosmos writes its history in scars. Some galaxies wear their history like a crown, and none does so more dramatically than the Sombrero Galaxy. Known for its striking resemblance to a wide-brimmed hat, this spiral galaxy 28 million light-years away dazzles with its glowing central bulge and crisp dust lane. But the real story isn't just in the disk we can see, it's in the invisible halo that sprawls around it, a vast sphere of stars, gas, and secrets stretching 10 times farther than the galaxy's visible edges. What makes this halo so extraordinary is its composition. Unlike the pristine hydrogen and helium that fill most galactic halos, the Sombrero's is laced with heavy metals. elements forged in the hearts of stars and scattered by supernova. This unusual richness points to a violent past, one where the galaxy grew not just by birthing stars, but by devouring its neighbors. Like a cosmic spider weaving a web of gravity, the sombrero likely absorbed smaller galaxies over billions of years, their stars assimilated into this shimmering shroud. The evidence lies in the halo's globular clusters, dense balls of ancient stars that orbit the galaxy like bees around a hive. Most galaxies have a few hundred of these clusters. The sombrero boasts nearly 2,000, an unrivaled swarm. Even more telling is their arrangement. Instead of orbiting randomly, many cluster along distinct streams. The skeletal remains of devoured dwarf galaxies, their stars still tracing the paths of their final orbits. It's as if the sombrero's gravity stretched these galaxies into luminous strands, leaving behind celestial breadcrumbs of its feast. Then there are the X-rays. Peering through the halo with space telescopes, astronomers have detected faint glows of high-energy radiation, the last whispers of gas heated to millions of degrees during past mergers. These X-ray emissions paint a picture of chaos, shockwaves rippling through the halo as incoming galaxies were torn apart, their gas compressed and heated to searing temperatures before cooling into the sombrero's embrace. But here's the puzzle. The sombrero isn't just a cannibal, it's a paradox. Despite its violent history, its disk remains remarkably undisturbed, a near-perfect spiral untouched by the turmoil around it. How did it gorge on galaxies without so much as a cosmic hiccup? The answer might lie in the way mergers unfold over eons. Smaller galaxies, stripped of their gas long before collision, could have been digested cleanly, their stars smoothly integrated without disrupting the disk. Or perhaps the sombrero's immense mass, a trillion suns, acted like a shock absorber, dampening the turbulence of each merger. Whatever the explanation, the sombrero's halo stands as a testament to the universe's relentless creativity. It shows us that galaxies aren't static islands, but dynamic beings, shaped as much by destruction as by creation. Every metal-rich star, every X-ray flicker, tells the story of a smaller galaxy sacrificed to build this cosmic masterpiece, a reminder that even in the void, nothing is truly lost, only transformed. Among the countless spiral galaxies adorning the cosmos, few are as strikingly perfect as the Whirlpool Galaxy, a celestial pinwheel spinning gracefully 31 million light-years away in the constellation Canes Venatici. Catalogued as M51, this grand design spiral isn't just photogenic. It's a cosmic blueprint, its arms unwinding like clockwork from a luminous core with such mathematical precision that astronomers consider it the gold standard for studying galactic structure. But what truly sets the Whirlpool apart isn't just its beauty. It's the gravitational dance it shares with its smaller companion, NGC 5195. A past due that's writing new chapters in our understanding of star formation. Peering into the Whirlpool's arms reveals a stellar nursery of staggering productivity. Unlike the ragged, disjointed spirals of isolated galaxies, M51's arms are crisp and continuous, dotted with clusters of young, blue stars that trace their curves like diamonds on a bracelet. These glowing knots aren't random, they're the result of density waves, gravitational ripples that sweep through the galaxy's disk, compressing gas and dust into pockets dense enough to ignite new stars. Picture a traffic jam in space where material piles up in slow-moving waves, triggering stellar birth in its wake. Yet the Whirlpool's prolific star-making owes much to its partner in crime. NGC 5195, a dwarf galaxy roughly one-third its size, isn't just orbiting M51, it's tugging on it, its gravity distorting the Whirlpool's outer arms into flowing streams of dust and gas. This gravitational interaction has turned the galaxy into a petri dish for studying cosmic collisions in action. As NGC 5195 swings past, it sends shockwaves racing through M51's disk, stirring the interstellar medium like a spoon in soup. The result, a surge of star formation so intense that the whirlpool's arms shine several times brighter than similar isolated spirals. But the real revelation lies in the details. High-resolution observations show how the companion galaxy's gravity has plucked tendrils of gas from the whirlpool's disk, stretching them into luminous bridges between the two. Within these filaments, newborn stars flicker to life, their radiation carving bubbles in the surrounding gas, a testament to the creative chaos of galactic encounters. Even more intriguing are the feathers, delicate structures of dust and gas that fringe the whirlpool's arms like lace. These are thought to be the fingerprints of magnetic fields, their invisible lines guiding material into intricate patterns as the galaxy spins. What makes M51 so invaluable is its role as a time machine. By studying its well-ordered spirals and the disruptions caused by its companion, astronomers glimpse how galaxies evolve over billions of years. The whirlpool shows us that even the most perfect structures are shaped by interaction. That solitude is rare in a universe where gravity binds everything together. And as NGC 5195 continues its slow orbital decay, destined to one day merge entirely with its larger partner, we're reminded that this dance is fleeting. The whirlpool's arms may be textbook perfect today, but like all things in the cosmos, they're just a snapshot in an endless reel of transformation. Some galaxies whisper their histories, but the Cartwheel Galaxy screams it. 150 million light-years away in the constellation Sculptor, this colossal ring-shaped structure spans 150,000 light-years, its vibrant blue outer band encircling a golden core like a cosmic bullseye. This isn't just a pretty shape, it's a galactic crime scene, the aftermath of a high-speed collision so violent it sent ripples through space-time itself. Roughly 200 million years ago, a smaller galaxy, perhaps a third the Cartwheel's size, plowed straight through its heart at nearly 200,000 miles per hour. The impact didn't just warp the galaxy, it rewrote its entire anatomy, triggering a chain reaction that turned a serene spiral into a starburst powerhouse. The secret lies in the shockwave. Like a stone dropped in a pond, the collision sent an immense pressure wave racing outward through the Cartwheel's disk, compressing vast clouds of hydrogen gas as it traveled. By the time this wave reached the outer edges, the gas had been squeezed so tightly it ignited into a frenzy of star formation. Today, that wave's footprint glows electric blue, a ring of newborn stars so massive and hot they outshine the rest of the galaxy combined. Each luminous knot in that ring is a stellar nursery, where thousands of suns ignite in clusters so dense they'd make our local Orion Nebula look like a quiet suburb. But the Cartwheel's true brilliance isn't just in its star-making, it's in the recycling. The same shockwave that triggered this stellar fireworks show also stripped gas from the galaxy's inner regions, flinging it outward like cosmic confetti. Now that displaced material is raining back down onto the disk in tendrils and streams, fueling future generations of stars. It's a snapshot of galactic renewal, destruction, and creation locked in an endless loop. Even the golden core tells a story. Deprived of its gas by the collision, it's now a quiet graveyard of aging red stars, their light a stark contrast to the youthful blue fury at the edges. What makes the Cartwheel so invaluable is its timing. Most galactic collisions are either too early or too late to study in detail, but this one's caught in the act. The outer ring, still crackling with newborn stars, shows us the immediate aftermath of the shockwave's passage. Meanwhile, faint spokes of dust and gas visible only in infrared trace the paths of material being dragged back inward, offering clues to how galaxies rebuild after catastrophe. It's as if the universe handed us a time lapse of galactic evolution, each frame revealing another layer of the process. Yet the Cartwheel holds even deeper mysteries. Recent observations reveal that its companion galaxy, the likely culprit behind the collision, isn't just a passive bystander. It's actively feeding the Cartwheel with fresh gas through a luminous bridge between them, a pipeline of raw material that could keep the star making frenzy alive for eons. This dynamic dance challenges the old notion of collisions as purely destructive events. Instead, the Cartwheel shows us how violence and creativity are two sides of the same cosmic coin, how chaos can forge beauty on scales beyond comprehension. Studying this galactic bull's-eye isn't just about unraveling one collision. It's about understanding the life cycles of galaxies everywhere. From the recycled gas to the newborn stars, the Cartwheel Galaxy is a masterclass in cosmic reinvention, a reminder that even in the vastness of space, nothing is ever truly lost, only transformed. Stretching like a cosmic comet across the void, the Tadpole Galaxy presents one of the most stunning spectacles of destruction and rebirth in the universe. Known formally as UGC 10214, this distorted spiral galaxy trails a 280,000 light-year tail of stars, gas, and debris, a streamer so long it could wrap around our Milky Way twice. But this isn't just a random scattering of celestial wreckage. It's a living textbook on the violent forces that reshape galaxies, written in starlight and hydrogen. The story begins with a close encounter, or more accurately, a cosmic sideswipe. Roughly 100 million years ago, the Tadpole Galaxy brushed past a smaller companion, their gravitational fields tangling like invisible fingers grasping at each other's stars. As the smaller galaxy whipped around its larger neighbor, tidal forces, the same pull that creates Earth's ocean tides, stretched the tadpole's disk beyond recognition. The outermost stars, caught in this gravitational tug-of-war, were flung outward, forming that magnificent tail. Unlike the orderly spirals we're accustomed to, these orphaned stars now drift in chaotic streams, untethered from their original galactic neighborhood. Here's what makes this debris trail revolutionary. It's a fossil record of galactic interactions. Within the tail, astronomers have identified clusters of blue supergiants, massive young stars burning fiercely against the darkness. Their presence is a puzzle. Normally, tidal tails contain only older stars ripped from their home galaxies. But these blue youngsters suggest something extraordinary. New stars are being born in the chaos. As gas compressed along the tail's spine, pockets dense enough to collapse under their own gravity ignited into stellar nurseries, proving that even in exile, the universe finds ways to create. The tadpole's tail also challenges our assumptions about galactic survival. Conventional wisdom held that galaxies losing mass to tidal tails would gradually fade. Yet observations reveal the opposite. The tadpole's core blazes with star formation, its rate 10 times higher than the Milky Way's. The collision didn't deplete it. The gravitational shockwaves funneled gas inward, supercharging its core like adrenaline to a heart. This burst of creation, known as a starburst, suggests that mergers aren't just destructive events. They're galactic rejuvenation sessions, triggering cycles of death and rebirth on unimaginable scales. Zooming in closer, the tail's structure tells its own tale. It isn't smooth but lumpy, with dense knots separated by near-empty gaps. These variations are time capsules, marking moments when the interacting galaxies' orbits shifted, each gravitational jolt imprinting itself on the escaping material. Some knots glow with the telltale pink of hydrogen nebulae, where ultraviolet radiation from newborn stars excites the surrounding gas. Others are eerily dark, their dust lanes so thick they swallow even the brightest starlight. This patchwork reveals a fundamental truth. Tidal tails aren't monolithic but mosaics, each fragment preserving a different chapter of the collision. Perhaps most remarkably, the tadpole's tail offers a preview of our own galaxy's fate. In 4 billion years, when the Milky Way and Andromeda collide, similar streams of stars will arc across space, celestial graffiti marking the merger. By studying UGC 10214 now, we're essentially peering into our future, watching how galaxies like ours might transform when gravity takes the wheel. The Tadpole Galaxy isn't just a spectacle, it's a laboratory. Every star in its tail, every wisp of gas holds clues to how galaxies grow, adapt, and survive in a universe where change is the only constant. Its 280,000 light-year trail isn't a scar, it's a roadmap guiding us through the tangled web of galactic evolution, one stolen star at a time. Locked in a gravitational embrace 300 million light-years away, the mice galaxies NGC 4676A and B perform a slow-motion passage that will one day mirror our own Milky Way's fate. These two spirals, nicknamed for the long, luminous tails stretching behind them like celestial rodents, are caught mid-collision, their dance preserving a snapshot of what happens when galaxies intertwine. Unlike the chaotic smash-up you might expect, their merger unfolds with eerie grace, stretched across hundreds of millions of years by the vastness of space itself. What makes the mice galaxies so mesmerizing are those spectacular tails, each over 100,000 light-years long, woven from stars, gas, and dust ripped free by tidal forces. As the galaxies swing past each other, their gravitational pull acts like a cosmic slingshot, flinging material outward in opposing streams. But these aren't just random debris trails. Within them, pockets of compressed gas ignite into brilliant blue star clusters, transforming the tails into rivers of newborn suns. It's a paradox, destruction birthing creation, as the very forces tearing the galaxies apart also seed them with fresh stellar life. Zoom in closer and the details grow even richer. The northern galaxy, NGC 4676A, still clings to traces of its original spiral structure, though its arms are now warped into elongated arcs. Its partner, NGC 4676B, fares worse, its core stretched and distorted, its disk unraveling like a spinning top losing momentum. Yet between them, a luminous bridge of gas connects the two, a testament to the material they've already traded. This isn't just a collision, it's a conversation, a give and take that will eventually erase their individual identities, blending them into a single, elliptical galaxy. The mice offer something even more profound, a preview of our cosmic future. When the Milky Way and Andromeda collide in 4 billion years, they too will sprout tidal tails, their stars flung into similar streaming arcs. But unlike the mice, which are relatively small and gas-rich, our galaxy's merger will unfold with even grander consequences. Andromeda's greater mass means its gravitational pull will warp our galaxy's disk more violently, while the combined gas reservoirs could trigger a firestorm of star formation, perhaps even igniting quasars in their cores. Yet the mice also hint at surprises. Recent observations reveal that their long tails aren't just passive debris. They shimmer with faint, intricate structures, filaments of dust, shock waves from supernova, even rogue star clusters drifting like boats on a stellar river. Some of these clusters are so young they must have formed after being ejected, proving that tidal tails aren't just graveyards but nurseries. Other regions glow with the soft pink of hydrogen nebulae, where radiation from massive stars excites the gas, painting the darkness with ephemeral watercolor hues. Perhaps most strikingly, the mice show us that mergers aren't in points, they're transformations. Long after their tails fade and their cores merge, the combined galaxy will bear little resemblance to its progenitors. New stars will burn where old ones once drifted, and the chaos of collision will settle into a stately elliptical glow. For now, though, the mice remain frozen in their dance, a fleeting moment of cosmic choreography that reminds us, even in the vastness of space, nothing stands still. Every galaxy, even our own, is just a temporary arrangement of stars waiting for gravity to rewrite its story. Some galaxies collide with a whimper, but the Antennae Galaxies scream. Officially catalogued as NGC 4038 and NGC 4039, this pair of spirals has been locked in a fiery embrace for the past 300 million years, their gravity twisting them into a shape that resembles the delicate antennae of an insect. As their disks interpenetrate, shockwaves race through colossal clouds of gas, compressing them until they ignite in bursts of star formation so intense they outshine entire galaxies. The antennae aren't just merging, they're birthing stars at a rate 20 times faster than our Milky Way, turning what should be a slow cosmic dance into a supernova-studded fireworks show. Dive into the heart of the collision and the numbers become staggering. Every year, these galaxies produce the equivalent of 30 solar masses worth of new stars, enough material to forge a sun-like star every 12 days. The most active regions, dubbed superstar clusters, pack hundreds of thousands of young, massive suns into spaces smaller than the distance between us and Alpha Centauri. These aren't just stars, they're stellar furnaces burning hot and fast before exploding as supernova in just a few million years. The energy released triggers chain reactions, compressing nearby gas and igniting more stars in a self-perpetuating frenzy. It's like lighting a fuse in a cosmic powder keg. Yet the antennae's real legacy isn't just starlight, it's the chemical elements they're scattering across the cosmos. Every supernova detonation peppers the surrounding space with heavy metals, oxygen, carbon, iron, even gold. Over time, these elements mix with the galaxy's gas, enriching future generations of stars and planets. The antennae are essentially cosmic alchemists, transforming primordial hydrogen into the building blocks of rocky worlds, and ultimately life. Telescopes have detected vast plumes of dust and metal stretching tens of thousands of light years from the collision site, proof that these galaxies are seeding their corner of the universe with the ingredients for new solar systems. What makes this merger so valuable to astronomers is its stage. The antennae are caught mid-transformation, offering a snapshot of a process that's normally too slow to observe. Their long, streaming tails, each over 60,000 light-years long, aren't just debris. They're time capsules preserving the history of the collision in their twisted filaments. Radio telescopes reveal dense knots of molecular gas along these tails, where gravity is already pulling the material into new stellar nurseries. Even as the galaxies tear each other apart, they're laying the groundwork for rebirth. But the most startling revelation might be the galaxy's cause. As the spiral's central black holes inch closer, their gravitational tug of war flings stars into chaotic orbits while superheated gas emits blinding X-rays. Eventually, these black holes will merge, sending ripples through space-time, but for now, their violent courtship floods the antennae with energy, further fueling the starburst. It's a reminder that destruction and creation are inseparable in the cosmos. The Antennae Galaxies show us the universe's relentless creativity. From the ashes of their collision come new stars, new elements, even new possibilities. They're not just a spectacle, they're a blueprint, revealing how chaos can forge the very materials that make worlds like ours possible. And as we watch their fiery dance, we're glimpsing a process that's shaped every galaxy, every planet, and every atom in our bodies. The universe writes its history in starbursts, and the antennae are one of its most vivid sentences. NGC 4194, better known as the Medusa merger, wears the aftermath of a cosmic cataclysm like a crown. This peculiar galaxy, 220 million light-years away in Ursa Major, is no serene spiral, it's a Frankenstein's monster of starburst fury and gravitational havoc. At its heart gleams a piercing eye, a dense knot of newborn stars blazing with the intensity of 1,000 suns, surrounded by twisting streams of gas and dust that resemble the serpentine hair of its mythological namesake. But this isn't just artistic coincidence, it's the signature of a violent encounter, where a gas-rich dwarf galaxy plunged straight through the heart of a larger spiral, leaving chaos in its wake. The Medusa's eye tells the story of shockwaves and resurrection. When the smaller galaxy struck, its impact sent ripples through the larger galaxy's reservoirs of hydrogen gas, compressing vast clouds until they collapsed under their own weight. The result, a starburst so fierce it birthed a superstar cluster, a single region crammed with millions of young, searingly hot stars packed into a space just a few hundred light-years across. These stars aren't just luminous, They're extreme, emitting ultraviolet radiation so intense it ionizes the surrounding gas, painting the nebula in vivid hues of pink and blue. Telescopes have even detected the faint glow of polycyclic aromatic hydrocarbons, complex carbon molecules drifting through the wreckage, the cosmic equivalent of soot left behind after a firestorm. Yet the real spectacle lies in the debris, stretching outward from the core like tangled ribbons. Tendrils of gas and dust spiral into space, some stretching tens of thousands of light years. These aren't random fragments, they're fossil records of the collision's geometry, tracing the path of the intruder galaxy as it tore through the disk. Within these streams, pockets of cooler gas have begun coalescing into new stellar nurseries, proving that even amidst destruction, the universe finds ways to rebuild. One particularly striking filament, dubbed the Medusa's braid, glows with the telltale signature of shock-heated hydrogen, its molecules vibrating from the violence of the encounter. What makes the Medusa merger so extraordinary is its timeline. Unlike slow-motion collisions that unfold over billions of years, this event was a sprint, a high-speed impact that compressed eons of stellar evolution into mere millions of years. The starburst we're witnessing is likely just a fleeting phase. Within another 100 million years, the core's furious star formation will exhaust its gas supply, leaving behind a glittering ball of aging stars. Meanwhile, the ejected streams will gradually disperse, their material either falling back into the galaxy or vanishing into intergalactic space. But the Medusa isn't just a relic, it's a preview. Our own Milky Way has its own dwarf galaxy companions, including the Large Magellanic Cloud, which may one day follow a similar fate. By studying NGC 4194, we're peering into a possible future, watching how galaxies cannibalize their smaller neighbors and repurpose the debris into something new. Every twisted filament, every newborn star in the Medusa's eye, whispers a universal truth. In the cosmos, destruction and creation are inseparable partners, weaving the tapestry of galactic evolution one violent encounter at a time. Flip a spiral galaxy on its edge, and suddenly its secrets spill into view. That's the magic of the Toothpick Galaxy, NGC 4565, a celestial needle stitching through the constellation Coma Berenices. From our vantage point, this cosmic marvel presents itself as a razor-thin sliver of light, its disk tilted a mere 1 degree from perfectly edge-on. What might look like a simple slash of starlight is actually a masterclass in galactic anatomy, offering astronomers a rare clean slice through a spiral's layers, free from the blinding glare of face-on views. Peer closer and the details emerge. NGC 4565's dust lanes, normally camouflaged in a top-down perspective, form a stark in-Chi stripe dividing the galaxy's glowing disk like a cosmic equator. These lanes aren't just aesthetic, they're cold, dense highways of gas and soot where future stars are already coalescing in the dark. Above and below them, the disk flares slightly, a subtle warp hinting at past gravitational encounters, perhaps with a long-vanished dwarf galaxy or an ancient brush with intergalactic gas. Such warps are common in spiral galaxies, but few showcase them as clearly as this one. But the real treasure lies buried at the Toothpick's core, hidden behind curtains of dust. A supermassive black hole weighing tens of millions of suns lurks, its presence betrayed only by the frantic orbits of nearby stars. Unlike the flamboyant quasars that blaze from face-on galaxies, NGC 4565's black hole is a shy giant, its feeding muffled by the edge-on orientation. Yet occasionally it coughs up X-ray flares, brief, violent outbursts that pierce the dust, offering fleeting glimpses of the monster within. These eruptions suggest that even quiet black holes like this one aren't so quiet after all. They snack when we're not looking. What makes edge-on galaxies like this so invaluable is their role as dark matter detectors. Because we see NGC 4565 stars moving in clean orbits along our line of sight, astronomers can precisely measure their speeds at different distances from the center. Those velocities reveal something startling. The stars orbit too fast to be held by visible matter alone. The only explanation, a massive halo of dark matter, an invisible scaffold enveloping the galaxy, its gravity gripping the stars like an unseen hand. Without this dark matter, the toothpick's outer stars would fling into the void. Yet NGC 4565 isn't just a scientific tool, it's a portrait of cosmic elegance. Its outer halo glows with the soft light of ancient red stars, while its disk shimmers with younger blue clusters, a generational divide frozen in starlight. And though we see it as a mere sliver, that sliver spans 150,000 light-years, half again as large as our Milky Way. It's a reminder that perspective changes everything in astronomy. What looks like a delicate toothpick from here is, in truth, a colossal pinwheel spinning in the dark, its secrets laid bare simply because we caught it at the right angle. For amateur astronomers, the Toothpick Galaxy offers another gift. It's bright enough to spot with modest backyard telescopes. Gaze at it, and you're not just seeing a distant spiral, you're witnessing the edge-on blueprint of our own galaxy. Because one day, far in the future, some alien astronomer might peer at the Milky Way from a similar angle, marveling at its dust lanes and warps, and wondering, just as we do, what stories its tilted starlight holds. Gaze at NGC 253, the Silver Coin Galaxy, and you'll understand why astronomers treasure its rare face-on orientation. Unlike the edge-on slivers that dominate our galactic atlas, this spiral in the constellation Sculptor presents itself like a gleaming silver dollar tossed onto the cosmic table, its arms unwinding in a near-perfect two-dimensional plane. That flawless alignment isn't just a visual treat, it's a scientific goldmine, offering an unobstructed view into the chaotic heart of one of the most active starburst galaxies known. Every detail, from its dust-choked arms to its seething core, is laid bare, revealing processes usually hidden by perspective. What makes this galaxy truly exceptional is the superwind roaring from its core, a titanic outflow of gas and dust hurtling into intergalactic space at millions of miles per hour. Imagine a hurricane scaled to galactic proportions. Shockwaves from thousands of supernova and stellar winds have blown open a chimney in the disk, funneling material outward in vast plumes visible in X-ray and radio wavelengths. These outflows aren't just cosmic exhaust, they're reshaping the galaxy's future. By ejecting massive amounts of raw star-forming material, the superwind could eventually starve NGC 253 of the fuel it needs to keep its stellar nurseries active. It's a self-limiting frenzy where the very fires of creation sow the seeds of their own dormancy. But the fireworks don't stop there. The Silver Coin Galaxy is a supernova factory, with astronomers detecting an average of one stellar explosion every few years, a staggering rate compared to our Milky Way's leisurely pace of 1 or 2 per century. This relentless demolition derby of dying stars has turned NGC 253 into a laboratory for studying stellar death. Each supernova leaves behind chemical fingerprints, heavy elements like iron and silicon, that pepper the surrounding gas, enriching it for future generations of stars and planets. Some of these explosions even occur in regions so dense with dust that they're only detectable by the heat they radiate in infrared, like flashes of lightning seen through thick fog. Zooming in closer, the galaxy's core reveals another puzzle, a supermassive black hole that's oddly quiet. Despite the surrounding starburst chaos, this black hole isn't feasting on gas to become a quasar. Instead, it seems choked, perhaps by the very superwind it helped create. The outflow may be clearing the galactic center so efficiently that the black hole is left starving, a cosmic irony where the energy of star formation stifles the monster it orbits. Yet for all its violence, NGC 253's face-on view gifts us with unexpected beauty. Its spiral arms, though choked with dust, glitter with young blue star clusters, their light diffused by intervening gas into a soft silver glow, hence its nickname. Dark tendrils of soot weave between these stars, tracing magnetic fields and shock fronts like ink dropped in water. And towering above the disk, those superwind plumes form a faint halo, a testament to the galaxy's relentless energy. Studying the Silver Coin Galaxy isn't just about witnessing an extreme environment. It's about understanding the life cycle of starbursts themselves. From the supernova that forge elements to the winds that sculpt galactic evolution, NGC 253 showcases the feedback loops that shape all spirals, including our own. It's a reminder that even in stillness, a perfect face on pose the universe teems with motion, a dance of creation and destruction written in starlight and wind. Among the cosmos' strangest optical illusions, Mayall's object, also catalogued as VV766, hangs in the void like a celestial question mark, its bizarre form challenging astronomers to decipher whether they're witnessing a galactic wreck in progress or a cosmic magic trick. First noted in the 1960s, this enigmatic structure resembles two glowing eyes connected by a faint, curving bridge, its symmetry so uncanny it feels almost deliberate. But the truth behind this peculiar shape sparks fierce debate. Is it a single galaxy torn asunder by tidal forces, or two entirely separate galaxies overlapping by chance from our vantage point, their light blending into this eerie silhouette? The collision theory paints a dramatic picture. If VV766 is indeed a single galaxy undergoing disruption, its eyes could be dense cores of stars and gas that have survived a close encounter with another galaxy's gravity, while the bridge between them represents the shredded remnants of their outer disks. Computer simulations show that when galaxies graze each other, tidal forces can stretch them into opposing knots connected by luminous streams, exactly what we see in Mayall's object. Supporting this idea, spectroscopic observations reveal that both eyes share nearly identical velocities, suggesting they're bound together in a gravitational dance. The bridge between them even glows with the telltale pink of ionized hydrogen, a sign of star formation triggered by colliding gas clouds. Yet the overlapping galaxy camp raises compelling counterpoints. Some argue the bridge isn't a physical connection but a line-of-sight illusion, where two independent galaxies, one in front of the other, align so precisely that their edges appear to merge. This wouldn't be unprecedented. The famous NGC 3314 illusion in the 1970s turned out to be two galaxies overlapping by chance, their distinct distances confirmed by later measurements. For Mayall's object, skeptics note that the eyes show subtle differences in star composition and dust distribution, hints they might belong to separate systems. Even the shared velocity isn't definitive proof. Galaxies in clusters often move in sync like schools of fish, creating false impressions of connection. The mystery deepens when we examine the object's infrared portrait. While visible light shows that haunting question mark shape, longer wavelengths reveal a more chaotic scene. One eye blazes with the heat of young stars, while the other glows with the cooler light of older stellar populations. If this is a single galaxy, why such stark contrasts between its halves? Yet if they're separate, why does the bridge between them contain gas that's clearly agitated, as if stirred by unseen forces? Perhaps the most tantalizing clue lies in the object's isolation. Most violent galactic encounters occur in dense clusters where frequent flybys are inevitable, but Mayall's object floats in a relatively empty neighborhood, making a chance collision statistically unlikely. Unless, of course, it's not a collision at all, but something rarer. Some theorists propose a third option. What if this is a polar ring galaxy, where a smaller galaxy was shredded into a hoop around a larger one, creating the illusion of a bridge when viewed edge-on? Such structures are vanishingly rare, but their existence proves galaxies can assemble in ways that defy simple categorization. For now, Mayall's object remains a Rorschach test for astronomers, its meaning as fluid as the theories it inspires. Whether it's a snapshot of a galactic car crash, a trick of perspective, or something even stranger, it underscores a humbling truth. The universe delights in shapes that tease our understanding, reminding us that even the clearest cosmic snapshots can hide layers of secrets waiting to be read. Stretching across the cosmos like liquid gold spilled on invisible canvas, the Molten Ring Galaxy, officially catalogued as SGAS-J 143845 plus 145407, isn't just a celestial oddity. It's a cosmic sleight of hand, a galaxy so perfectly aligned behind a massive foreground cluster that gravity itself has twisted its light into a dazzling, fiery loop. This phenomenon, called gravitational lensing, occurs when the immense mass of a galaxy cluster warps the fabric of spacetime so profoundly that it acts like a magnifying glass, bending and amplifying the light from objects far behind it. In this case, the lens has transformed a distant, ordinary galaxy into a shimmering arc, one that holds secrets about the universe's youth too faint to see unaided. What makes the Molten Ring priceless isn't just its beauty, but its distortion. The galaxy's light, emitted when the universe was barely 3 billion years old, has been stretched, duplicated, and smeared into multiple images by the lensing effect. Astronomers can exploit this cosmic quirk like a forensic tool. By comparing the different paths the light has taken around the foreground cluster, some slightly longer than others, they can reconstruct the galaxy's true shape while simultaneously mapping the distribution of dark matter in the lens itself. It's like solving a puzzle where the pieces reveal two pictures at once: the distant galaxy's structure and the invisible scaffolding of the universe. The data extracted from this golden mirage is staggering. Analysis of the molten ring's warped starlight suggests it's a bustling factory of young stars, churning them out 10 times faster than the modern Milky Way. Its spiral arms, magnified to unprecedented clarity, show delicate dust lanes and nascent star clusters, details usually lost in the blur of such vast distances. But the real treasure lies in the galaxy's chemistry. Spectroscopic studies reveal telltale signatures of heavy elements like oxygen and carbon, forged in the hearts of earlier stellar generations and expelled into space by supernova. These elements, the raw materials for rocky planets and potential life, are far more abundant than models predicted for galaxies this early in cosmic history. The Molten Ring challenges our timeline for when the universe became chemically complex. Yet this lensed wonder offers even broader gifts. Gravitational lenses like this one function as nature's telescopes, granting us access to galaxies otherwise too distant or dim to study. The foreground cluster, acting as the lens, magnifies SGAS-J 143845 plus 145407 by a factor of 20, equivalent to observing it with a hypothetical telescope mirror 300 meters across. This cosmic zoom lets astronomers probe an era known as cosmic noon, when star formation peaked across the universe. By comparing lensed galaxies to their modern counterparts, we can track how galactic ecosystems evolved over billions of years. The Molten Ring also holds clues to one of astronomy's greatest quests, mapping dark matter. The precise way the galaxy's light bends depends on how mass, both visible and invisible, is distributed in the lensing cluster. Tiny discrepancies between the predicted and observed distortion hint at dark matter's granularity, potentially revealing whether it's cold, warm, or something even stranger. Some theorists speculate that anomalies in certain lensed arcs could even point to exotic physics, modified gravity, or hidden dimensions, though the Molten Ring hasn't yet betrayed such radical secrets. Ultimately, this golden mirage is more than a pretty anomaly. It's a bridge across time, a chance to scrutinize the universe's formative years with a clarity no human-made instrument could achieve. And as astronomers discover more of these gravitational mirages, each a smudged fingerprint of cosmic architecture, they piece together a deeper truth. that the universe's most powerful telescopes were built not by human hands but by gravity itself, sculpting light into magnified masterpieces we're only beginning to decode. Tucked away in the cosmic archives, the green pea galaxies stand out like emerald freckles against the darkness, tiny, brilliant, and utterly perplexing. Discovered by amateur astronomers combing through Galaxy Zoo's crowdsourced data, these compact powerhouses pack the firepower of entire galaxies into spaces barely 1/10 the size of the Milky Way. Their vivid green hue, captured in telescope images, isn't just a visual quirk, it's the telltale glow of oxygen atoms, supercharged by intense ultraviolet radiation from newborn stars. But what makes these cosmic peas truly extraordinary isn't just their color or size. It's the window they offer into one of the universe's most pivotal eras, the epoch of reionization, when the first starlight pierced the cosmic fog. Rewind nearly 13 billion years, and the universe was a murky soup of neutral hydrogen gas, absorbing light like a thick interstellar blanket. Then something changed. The first galaxies ignited, their fierce radiation stripping electrons from hydrogen atoms in a process called reionization, transforming the cosmos from opaque to transparent. The green peas, though much younger than those pioneering galaxies, behave like their modern-day analogues. Their star formation rates are off the charts, with some churning out new suns hundreds of times faster than our Milky Way. Each of these stellar newborns blasts space with ultraviolet photons, mimicking the conditions that once ionized the universe. Studying them is like finding a time capsule, a chance to witness the engines that reshape the cosmos in miniature. Yet the peas' significance doesn't end with reionization. Their oxygen-rich spectra reveal another critical role. They're cosmic alchemists, peppering the universe with heavy elements essential for planets and life. When massive stars in these galaxies explode as supernova, they scatter elements like oxygen, carbon, and iron into the void. Unlike larger galaxies where these metals might sink into dense cores or get lost in vast gas reservoirs, the peas' small size means their enriched material gets ejected easily, seeding intergalactic space with the building blocks of future solar systems. It's a paradoxical twist. These diminutive galaxies might contribute more to cosmic chemistry than their larger, more imposing cousins. What's even more surprising is their rarity. Despite their outsized impact, green peas account for less than 0.1% of galaxies in surveys. Their scarcity suggests they represent a fleeting phase, perhaps a galaxy's adolescent growth spurt, when a sudden influx of gas triggers a frenzied burst of star formation before settling into calmer adulthood. Some astronomers speculate they're the precursors to today's dwarf galaxies, their fiery youth eventually giving way to a quieter existence. Others wonder if they're the result of galactic collisions, their compact fury ignited by the shockwaves of mergers. Then there's the puzzle of their structure. Most galaxies, even starbursting ones, have orderly rotations or predictable shapes, but green peas are chaotic. Their gas and stars churn in turbulent, asymmetric blobs. High-resolution images show they're pockmarked with supernova bubbles and radiation bubbles, their interiors more like storm-tossed oceans than the serene disks of spiral galaxies. This turbulence might be key to their prolific star formation. The constant collisions between gas clouds create dense pockets that collapse into stars like sparks from a grindstone. Yet for all we've learned, the green peas guard their secrets closely. Why do some galaxies enter this hyperactive phase while others don't? How exactly do their metal-enriched winds escape into intergalactic space? And could there be even smaller, fainter versions lurking undetected, playing an even greater role in reionization than we've guessed? Each answer peels back another layer of the universe's history, revealing how the smallest galaxies might have wielded the greatest influence. The green peas remind us that cosmic importance isn't measured in size. These tiny, glowing specks overlooked at first, then celebrated as Rosetta Stones of the early universe, prove that sometimes the most profound truths come in the smallest packages. They're not just oddities, they're proof that the universe's grand narrative is written in starlight, chemistry, and the relentless ingenuity of gravity. From the haunting symmetry of Hoag's object to the vertigo-inducing scale of the Hercules-Corona Borealis Great Wall, these 25 galactic enigmas aren't just celestial oddities, they're cosmic breadcrumbs, each one leading us deeper into the universe's greatest mysteries. Every peculiar ring, every inexplicable void, every galaxy spinning the wrong way forces astronomers to question what they thought they knew. It's as if the universe is leaving clues, daring us to piece together a puzzle we don't yet fully understand. Take the Boots void, for instance, an emptiness so vast it defies logic, or the Fermi bubbles towering over our own galaxy like remnants of a forgotten eruption. Each discovery starts with a simple question: how can this exist? And that question ripples outward, reshaping theories about dark matter, black holes, even the very fabric of space-time. The green pea galaxies, tiny but fierce, rewrite the story of how the first stars lit up the cosmos. The dark flow tugs entire clusters toward something beyond our sight, hinting at realms we may never map. These aren't just anomalies, they're catalysts pushing science forward one paradox at a time. What's thrilling is how much we still don't know. The Great Attractor lurks behind a veil of dust, its pull undeniable yet its nature unclear. The Cartwheel Galaxy's perfect ring shows us how violence can birth beauty on a scale beyond comprehension. And the molten ring, warped by gravity into a celestial mirage, proves that sometimes the universe itself becomes our telescope, bending light to reveal its secrets. So here's the real wonder: every time we solve one cosmic riddle, two more take its place. These structures aren't just landmarks, they're invitations to keep exploring, to stay curious. Which one captivates you the most? The eerie silence of the Boots void, the hypnotic dance of the mice galaxies? Drop your pick in the comments, and let's keep the conversation as boundless as the cosmos itself. Because the universe isn't done surprising us, not even close.